So today and next time, we're going to be dealing with some data structure related issues. And so what I want to do is talk about a new design pattern, the adapter design pattern. And to illustrate its use, I'm going to use a priority queue. So probably 90% of the time when I use a collection, I'm probably just going to use array list. 8% of the remaining 10% will be a priority queue. So those are the two most frequent things that I use when I'm using a data structure just for to do something, make a game, whatever I'm building at that particular time. Those I use most frequently. Unfortunately, I don't think in data structures it gets emphasized as much as it probably should. So I'm going to use this opportunity to try to make up for some of that. But first we need to talk about how we're going to compare items. And I've got this class called keyed item. We're going to make it increasingly useful as we work our way through the semester. But right now, all it is it contains a string that's going to be the key. So the objects that we want to sort, which we need to do for a priority queue, we need to do some kind of sorting or be able to compare items to each other. We're going to make sure that each one of if it's an object that we want to be sorted somehow, we're going to make sure that it has a key. Okay? Because this is the thing that we're going to use. This key thing is going to be the item that we're going to use to compare items. Okay? So whenever we want to compare two objects, we're going to pull out object 1's key, we're going to pull out object 2's key, and then we're going to compare the keys to figure out who needs to be sorted relative to the other, which object goes in front. Okay? So there's a constructor that accepts a string that we copy into our variable here called key, but more importantly, there's a getKey method. That simply returns the key. Okay, now remember that strings are immutable, so I don't really have to worry if I use this system, if I use the key item class correctly, I don't have to worry about this key getting changed. Because if I put a bunch of items in, say, a tree, and my user has references to some of those objects at various locations in the tree, they could just change the key and then my tree's all messed up. Okay, it's no longer sorted with respect to the keys. So we've got to be careful when we're using this class to make sure that when we define our key, that it's something that's immutable. And so the obvious thing, the thing that's built in for us that's already immutable is a string. Okay? So we'll make this more useful later on, but for right now, and then eventually we'll get rid of it for another preferred method altogether. But right now it just contains a string. So we're going to put a bunch of keyed items on our priority queue, and we want to sort them. We're going to sort them by key. Okay? All right, so what about comparisons? The way you do comparisons for strings, which remember when we pull the keys out, they're strings. The string class has a compare_to method, or maybe even more usefully, we can call this key1 and key2. Okay? And so assuming we've already asked, we're trying to sort two objects. We've already asked each one of those objects for their keys. And now, how do we use this method? Well, this method will return a number less than 0. So compare_to returns an int. So if we look at the method signature, for strings, it returns an integer. Okay, so one of the strings is calling the compare_to method. The other string gets passed in as a parameter. So if it turns out when we compare those two strings, and let's say that key 1 was ABC, and key 2 was DEF. Okay, very creative. Let's suppose those are the keys. And we run this statement, abc.compare_to_def. Okay, we will in fact get a number less than 0, which says that alphabetically, the object associated with key 1 should come first in this list relative to the object represented by key 2. Okay, so strings doing alphabetical sorting, which is really using the ASCII table to compare who should go first. Okay? If the two keys are completely identical, we're going to get a 0 back from the compare to method. That means on a character by character basis, they're exactly the same. On the other hand, what if they're close but not quite the same? Suppose this one was A, B, D. What do you suppose I would get? Would I get less than 0, equal 0, or greater than 0?
Greater.
Okay, it's still going to be less than 0 because we're going to see the first two characters match, we move on to the second character. The second characters match, we move on to the third character. C comes before D, so we return a negative number. In fact, that negative number is going to be -1 because the difference in the ASCII code for lowercase c and the ASCII code for lowercase d is 1. They occur next to each other in the ASCII code table. Okay? However, you never need to know that number. Okay? You only need to know if it's positive, negative, or 0. But it does return the difference in ASCII code values of the characters, the first non-matching character that it found. If they all match, of course, that means return 0. So if it had been ABC, ABC, we would return a 0. Okay? What do you suppose would happen if I change that one to capital A and everything else is exactly the same? Just make that be a C.
I bet it'd still return a 0.
Okay, there probably is a way that we could make that to treat these as they're identical. By default, it doesn't. This is tricky. You would think that it would be less than. You would think that the ASCII code values for the lowercase letters are smaller than the ASCII code values for the uppercase letters, but in fact, that's not the case. Okay? So this guy wants to be in front because capital A has a smaller ASCII code value than lowercase a. So that means if they're out of order with respect to each other, we're going to get a positive number. Okay, which happens to be 32 in this case. The distance between the uppercase and lowercase letters, I think, is 32. Okay? So we don't care about the absolute number, even though I brought it up twice. We only care about that. So that's how we're going to do comparisons. Now we're going to make that increasingly, that's very limited what we're doing right now, just comparing strings. We're going to make this increasingly more object-oriented as we learn to do more advanced techniques. Remember, the polymorphism, inheritance, and encapsulation, the only one we've talked about so far is encapsulation. So we've got some ground to cover before we know enough techniques to improve on this system. But we know enough now to get started. So I want to come here and talk about what a priority queue does. Hopefully most of you remember what a priority queue does. It has some properties of queue, but there are several important differences. So a priority queue, when you remove an item, from a priority queue, which I'll abbreviate PQ, the smallest item in the collection is returned. Okay? Now we could make this so that it returns the largest item. The difference is one of them we call a min priority queue if it returns the smallest item, which is the usual thing, versus a max priority queue which returns the largest item. Okay? And if there's a bunch of ties, how those ties are resolved depends on how we built the priority queue. Okay, so we may decide once we're building this thing that we want particular behavior if two strings are exactly the same. We do a comparison, we get 0. We may want to enforce the behavior, maybe we don't care. We just leave it the current order. We're just not going to do anything if they're exactly the same. But those are some details that we can decide on when we're actually building the thing. So that's the basic idea. You have a collection of a bunch of items. When you insert them, we don't really know what's happening. We could either we could do a lot of work when we insert items in the priority queue, or we can choose to not do any work. Be lazy for insert. But either inserting or removing from the priority queue, one of those two methods is going to have to do some work in order to make the property that when we remove an item, the smallest item is returned. Okay, so it depends on what we do for insert, what's going to happen for remove. If we do more work in insert, then there's less work in remove. If we do no work in insert, there's more work in remove. Okay? But that's the essential property of a priority queue. Okay? So we have to have some way of comparing items, and that's where that keyed item thing comes in, and why I talked about comparing strings. All right. Let's build our priority queue. So I am just going to scoot all this stuff down, and we're going to write it again. So I get to write it twice. Okay? So you can see down there at the bottom that I've decided to build this thing out of an array list. In fact, let's just do this. We'll leave that. Okay. Hopefully you guys in your data structures class, you talked about, well, you can build a stack out of an array list. You've got data structures that can build on other data structures that you created earlier in the class. Okay? So I could make a priority queue out of just a regular old array. I could have done this. Okay, I could have just used a regular old array. The problem is with the priority queue, I would really prefer not to have any maximum limit on the number of items that go in there. Okay? So if I'm using an array directly, if the array fills up, then I got to have the tedious code to resize it, copy over the elements, and all that jazz. Okay? So on the other hand, I know that all of that work's already been done for me. So we're going to make use of it by using composition. We're going to create a Pqal. By the way, this naming convention is the stuff on the left is what the data structure actually is. The stuff on the right, the AL part, is how we're going to implement it. Okay? So that's sort of the convention that I used in data structures and carried over in here. So Pqal, that tells you what it is I'm trying to create. And oh, by the way, I also tell you what the implementation is. Okay? So if you remember the pros and cons of the various things, then you can decide which one you need based on the name of that particular class. All right. So ArrayList does all the resizing for me, so let's not reinvent all that stuff. Let's just use an array list. And we're going to be putting keyed items in there for now, so nothing. Eventually, of course, we want to be able to put anything in there. Okay? If I want to put spaghetti in there, I have a spaghetti class. If I want to put tires in there, socks, whatever the case may be, I would really like to plunk that, have a way of making that array list work for that specific object. Well, that's next time. Okay? So for today, let's just say the only thing that we're ever going to put in this priority queue are keyed items, which of course would really be a waste of time, of effort for me, because if I decide I need to put pizzas in there, I got to write a Pqal that takes pizzas. Okay? So the idea for our lecture next time is kind of like templates, only in Java they're called generics. Write one class and make it flexible enough to where I can specify any object type to use that particular class. Okay? So here's our array list. Our default constructor simply creates an empty array list. I don't have to worry about my user having a reference to that thing because the constructor doesn't take any parameters. So the fact that I made this private means I should have, this looks like the encapsulation is going to be correct. I've limited the ability for outside users to mess up with that. They can change it, but only through the methods that I provide, which are the priority queue methods. Okay? So we have a constructor. We're going to need to be able to ask the priority queue if it's empty or not. There's a couple of ways that we can do that. Okay, I could do a size variable here and initialize it to be 0. And whenever the user adds an item, increment size. Whenever the user removes an item, increment size, decrement size, return, and then inside here, return whether or not size is equal to 0. Okay? Could have done that. What can I do instead? I don't really need this variable. In fact, it's kind of silly for me to put it in there. Pardon?
Return items not size.
Yes. So we're going to use delegation. Good. Okay? Whenever we're using a fairly complicated object as part of composition, you're probably going to want to use delegation. Okay? Or you probably didn't design it very well. So if you've got a good design, then there's probably a lot of stuff that you can have those objects do for you that you don't have to repeat. Okay? Well,
Do you have to type a Boolean, or can you just put bool when you're coding?
Yeah, it's Boolean in Java. Yeah, sorry. Okay? And I don't know if y'all talked about in C++ you can get away with this. Okay, that causes weird errors though if you're not, unless that's exactly what it is that you meant to do. If you really meant to do that. Okay? Well, in Java, they took care of that. This will generate an error or a warning or something like that. And so we got to do a comparison operator because the result is supposed to be a Boolean because that's what I said this method returns. Okay? All right. We have to have a way of putting stuff into the priority queue. So I also have to have another public method, which is going to be void. And the only things that this particular priority queue takes are keyed items. And I'm going to make the decision for you that I'm going to be super lazy and I'm not going to do much work here for PQ insert. So if I want to complete PQ insert in one line, what's it going to look like? Okay. In fact, adding to index 0 is going to be slow. Why is adding to index 0 for my array list going to be slow? It's got a shift. So if I've got 100,000 items in there, that's some wasted time. Okay? So I would prefer to add to the end. So I could compute what that index is using size, or I can use the fact that there's automatically what's called a convenience method, that if I don't provide an index at all, it knows I'm trying to add on to the end. Okay, so what's the order notation if I do this? Yes. Okay? So we've chosen to make PQ insert be the efficient operation. Okay? Probably a bad choice, but good enough for now. Now, we discussed what's supposed to happen when I do a PQ remove. And it's supposed to return the smallest item. Well, the only thing that we've got stored in here are keyed items. So that's what I'll return. And I don't specify, I don't pass in an object or anything, because I'm going to let the priority queue find the smallest item for me and then return it. Okay? Well, since we were lazy for insert and all of our items are completely scrambled up, just completely dependent, well, if I add them in there in ascending order, hey, they're already sorted. Okay? That would be great. But most likely, if I were, going to test your program, I'm not going to insert them in sorted order. I'm going to randomize them up pretty thoroughly, and then make sure that your PQ remove method gives me the smallest item back first. Okay? So they're all scrambled up in there. There's no sorting done whatsoever because we decided that PQ insert should be fast. So we made it fast. Okay? How am I going to find the smallest item? I'm going to have to do some comparisons. What is the order notation for this method going to be? Okay, it's not n squared, but let's put n squared up here. If I sorted them here, as you guys know, the slow sorting algorithms are n squared. What are the fast sorting algorithms? N log n. What's a search? N. What's a binary search? Okay, can we do a binary search? Okay, no we can't, because the items aren't sorted. A prereq for a binary search is that the items are sorted. So we can do a linear search, which is what we're going to do. Okay? Let's think about the alternative. Suppose I decided to do the work for PQ insert and PQ remove is order 1. So if they're sorted, then I know that the smallest item, if they're sorted in ascending order, which how long would it take me to sort to sort as an item comes in? Next item comes in. How long does it take me to sort it? Not very long. Yeah, give me an order notation. In. Okay, I was expecting you to say n squared again. You let me down. Okay, it's not n cubed. Okay, now we're going crazy. Exponential. Okay, factorial. Okay, it's n because now the reason why you're slow at sorting algorithms in data structures were n squared is because you're trying to sort the whole thing. Here, I'm adding one more item in there. Okay, so all I got to do is potentially, can I use a binary search now? In fact, someone said log in. Can I use a binary search now?
Yes.
I can, as a matter of fact. So we can do even better. We can make that be log in because I'm assuming everything that's already in there is sorted. And it's sorted, and we're using an array. So conveniently now, I can do I can compute my mid-index and all that fun stuff that you do for binary search. Okay, there is a subtle reason why that's actually not what I would do if I were writing this class. But for your purposes, yeah, we can actually do a little bit better if we sort and insert, and then I know which index contains. What's the order notation if the smallest item is at index 0? Okay, unfortunately that's n. That was a trick question. If the smallest item is at index 0, what happens when I remove it? We discussed this already. We have to ship. So if I were trying to make this as efficient as possible, I would put the smallest item at the end, and I would end up with order log in for one operation and order 1 for the other, which is a small improvement over what we did, or what we're going to do, like this. Okay? So actually there's a subtle reason why log in won't quite work for insert, but we'll get to that later. Okay? All right. So I got to do a linear search, which means we're going to have to do some comparisons. So what should I do if the array list is empty? So the first thing I'm going to do is I'm going to check to see, do I even have anything to do here? Okay, I've got to return an object, but I don't really have an object to return, so I'm going to return null. Okay, and now that might upset your users who, get null pointer exceptions when that's happened. So of course that's something that we would have to document, but we'll talk about the documentation in a later class. So we got a special case there. What about if there's only one item in there? Return it. It's going to be at index 0 of my array list. Okay, we may not need that special case, but we will need this special case. Okay, so if there's nothing in there, just don't try to do anything. You're going to get a null pointer exception. Bad stuff's going to happen. Okay, if there's one item in there, we could probably make our algorithm work. But just in case, for now, let's say if there's only one item in there, well, I know where it is, but I don't want to just return it, so that's not quite right. I do want to get a reference to it so that I can return smallest, but what do I have to do in between those two lines? Remove it. In fact, isn't it the case that remove will return a reference to the item? Did you guys figure that out in one of the labs? Does that work?
Yep.
Okay. I'll take your word for it. Okay. items.remove, and then that needs to be a 0. Okay? Frequently, data structures don't necessarily have the remove method behave that way. Sometimes remove is void, so you have to get the item first and then remove it. It just depends how that abstract data type was defined. Okay? And I never remember which ones do it and which ones don't, so you guys know better than me. Okay. So now we need to start. So now here's our algorithm. We're going to set the smallest to be items at 0. Okay? I don't know if it's actually going to be the smallest or not yet. And then I'm have a loop. And I also need to keep track of the smallest index. Okay, so I get a reference to what I think the smallest item might be, and I get a reference to that current index. Okay, so at the end, when I figure out what the smallest index is, I can just grab that item out and return it. Okay, and I'll have to remove it just like I did up here. But while we're ongoing, I don't want to remove anything. So I'm only going to be using gets while we're doing our comparisons, and only at the end am I going to remove the item at smallest index. Okay, that's not quite right. So we're basically going to do a linear search here. And we need to get the next item. Whoops, we can go to 1, right? And let's store the integer that's the result of our comparison in score the result of our comparison in an integer, and then test it whether it's less than 0, greater than 0, or equal 0. Okay, to determine whether we need to update smallest index to be our current index, I, or not. So we've got smallest dot compare to test. Okay. If compare, in fact, let's reverse that. I'll explain why. Maybe, if I feel like it. Okay? So I like to set this up so that if the calling object is smaller, I guess since we're starting at index 0, I just don't like having smallest being the calling object in this particular case. So if we get back, so with it aligned like this, with the calling object being the one we're testing, and smallest being what we believe the current smallest to be, what am I going to do if compare is less than 0? What does that mean? That I need to update smallest to be test. Okay? It's supposed to come before what I thought smallest was supposed to be. So I can do that. Whoops, that should be I. Okay? So we need to go through that and test it. We're skipping index 0, but go through all the other indices in our array. And hopefully by the time our for loop is completed, we now know the smallest index. Okay? In fact, we took out test here already. Whoops, smallest. Okay? So we actually have smallest already points to test. Why did I need the index as well? I already know the smallest one. Can I just return it? Yeah, so I can remove it. So before I return, I've got to go in there and do an items.remove smallest index. Now here's a case, so even though you guys told me that remove returns an item, I don't really need it, so I can ignore it. Okay? I don't really need it because I already had a reference to the smallest up here. I just needed to know remember what I was, or the smallest index was, so I can return it. This is one of those very rare cases. So when I give you a general principle like making all your instance variables be private, that doesn't mean 100% of the time, but it probably means 99% of the time. Every once in a while, you got a case where you don't actually need to use the return value. But for your purposes, even if you put it on there and ignored it, or, I mean, there would be nothing wrong with you to say, had you done this, it's still the right answer. Okay, you're getting a reference to the thing that you already had a reference to. Okay, but I actually don't have to do that because I already have a reference to it. All right. So we can see in here that since we had to do a linear, to find the smallest item, we had to do a linear search. And we're going to have to continue to do that every time that we want to remove because we haven't done any sorting. So we did find the smallest item and took it out, but still the rest of the items that are still there are all scrambled together, so we'll have to start over from scratch and find the next smallest item. Okay? But we could have made this method be really short if I had actually done some sorting inside PQ insert. Do some comparisons to find where the next item is supposed to go. What kind of sort is that when I look through to find where the item is supposed to go? Let's insert. It's insertions. It's one step of insertion sort. So actually, the way I write this would, if I were to do this for real, I would make my insert do insertion sort. But of course, it's just one iteration where I find where the next item is going to go. Now, eventually, I'll have to sort them all, but I don't know when the next item is going to come in. It might be a while. Okay, maybe the user's got to click on some brass cards or something before that happens. But eventually, the next item will come in, and I'll do an insertion sort step on it. So it really is insertion sort, but what you're used to doing in class is that you did them all. Okay, you did them all within one algorithm. Now we only do one step of it whenever we get a new item to sort. That sounds important.
It is important. My bad.
It's all right. I won't have a hissy fit. Okay. Okay, so now, yeah, that looks roughly the same. Okay, we'll go with it. So now let's assume that, the rest of the stuff that I'd already put in there works. We'll find that out whether it does or not in a minute. And let's just run it. So let me show you the driver. So I've got some strings, and I'm inserting them in, which they're all going to be fast operations because I'm simply going to put it at the end of the array list. And the way I like to process my priority queues when I'm pulling stuff out is just use the isEmpty method. So as long as the priority queue has stuff left in it, call the remove method to get the item out, and then print it out. So I expect them to come out of this thing in sorted order. So I think I'm set up to test that. We will find out. Nope, not set up to test that. Okay, so fortunately, that looks sorted. All right, so what do I like to use priority queues for? Well, it's kind of right in here. Okay, priority queues are I really like priority queue sort. I don't know if you guys did that in data structures, but if you have a working priority queue, hopefully built more efficiently than ours. In fact, let's talk about that for a second. This is actually pretty crappy. Okay, this is a really horrible way to build a priority queue. Although it makes use of the thing that I told you I use 90% of the time, okay, which is an array list. In reality, we're going to want to do something much more efficient, like suppose I built this thing out of a AVL tree. Yeah, fond memories, huh? Okay. Suppose I built it. So if I now create a tree up here, and I insert, this is actually a good exercise, and I insert an item I do a PQ insert, how long how many statements am I going to have in here to put that thing in the AVL tree? AVL tree dot insert item, and then not have this one. Is that going to be sorted? Yeah. So all that work, all that nightmarish stuff that you guys went through on AVL trees is useful here. You've delegated all that stuff to the AVL tree, and now you've got a one-line thing that in fact sorts, where ours didn't. So you've got an auto sort for your PQ insert. Okay? What is the order notation for inserting an item in an AVL tree? Log in. Okay, remember AVL trees are balanced, so the longest path from root to one of the leaves is going to be log. Okay? So that's a pretty fast insert. And what about remove? Where is the smallest item? It's all the way left, right? Left, right, no. All the way left. Until you can't go left any further, you found the smallest item. What's the order notation for finding the smallest item? Log in. So we would have log in, which is better than order one, order in, no matter which way we did it. Okay? So that would be an improvement, and it would be almost completely all delegation. We can simply ask the AVL tree to remove. We'll give it the search key. It goes and finds the leftmost item, returns it to us. So remove is only going to be a couple of lines at most. Okay? So all that time that you spend on AVL trees, you can actually start to use, hopefully in this class. If you didn't in data structures, hopefully you will in here. Okay? So there are some structures like that that are provided by Java, like ArrayList, but they don't quite, they get further and further away from the exact kind of method signatures that I like and you probably used in data structures. Okay? So now, so we can do better. We can use a more sophisticated data structure to build a priority queue and have it be more efficient. So assuming that we did that, and this is all super efficient, now I can use my priority queue to sort. Okay? So as long as I'm using something reasonably efficient and not ArrayList, an unsorted ArrayList to do my priority queue, I can use it to sort. And all I have to do is dump all the items into the priority queue, I probably pass in an array or something, just loop over all the elements in the array and call PQ insert on every one. And then have a while loop just like this that says remove the first one, which is going to be the smallest, put it back in the array. Remove the next one, it's going to be the second the smallest, put it back in the array. So essentially you got a for loop to dump them all in and a while loop to pull them back out, putting them in the array in sorted order. Okay? And so that's also an efficient sort if your priority queue is built using something like an AVL tree. Okay? Now, all the way back to the slides where I talked about the adapter design pattern. We did it. In fact, you saw two examples of the adapter design pattern. The first one, so we knew what was required for priority queue. We were told what the requirements are. We need an isEmpty method, we need an insert, and we need a remove, where the remove is supposed to return the smallest item. We were told those things. Now, we could have just written the whole thing using an array, which is what I started out with. Okay? But instead, we chose to use delegation, where we had to do very little work, here, for either one of these, but in particular the array list. So we'll go back to the array list for now. Okay? So we've got one line of code there. How did I implement that method? I used the required method signature, which my users are going to see documentation for and expect to be able to call exactly the way they see there. So I've used that, but inside there, I made use of, because of my encapsulated array list, I made use of the array list method signatures. So we've adapted the array list method signatures to be used for a different set of method signatures. Okay? And so that's the adapt. So one's called insert. I use an add to actually implement it. Or whatever you use to insert an AVL tree. If we decide to implement this thing with an AVL tree, our adaptation, the priority queue methods don't change, but the adapted methods inside there are going to change to conform to the methods available for whatever data structure we decided to use. Okay? The more work you put into the underlying data structure, the less work you're going to have to do here. So all that effort that you spend on AVL trees is really not wasted. Now you can start doing one-line methods that are totally efficient. Okay? All right, same thing down here, although it was difficult for us to do that adaptation. We still used get. We still used remove. We still used the moves, the methods that were provided for us by ArrayList to implement this new method. But it was complicated because of our choice of data structure. Okay? Usually when you use the adaptive design pattern, you have 1, 2, 3 lines inside the methods because the thing that you're adapting to has all the complexity already built into it. Okay, so you're doing mostly just straightforward delegation. We delegated completely in both of these cases. We couldn't delegate completely in this case because ArrayList wasn't sophisticated enough to handle that operation, to handle the adaptation to priority queue remove. Okay? Had we done AVL tree, it would have been a couple of lines. Maybe it's 1 line. Okay? Now, eventually, we would have to add a little bit of extra stuff in there to check for exceptional situations. You know, something goes wrong. That can certainly happen. But we haven't covered the syntax for that, and it's pretty, involved. So we're going to have, 1 or 2 lines for our delegated methods, depending upon how sophisticated this thing up here is. Okay? So that is the adaptive design pattern. And let's see if there's any other ways that we could have implemented. So we talked about using priority queue with an array list, and we saw that that was order 1, order in, or maybe log in if we decide. Oh yeah, so that reminded. Do we have time? Yeah, we got time. Okay, so that reminded me. I wanted to talk about. Okay, when we did the sorting in insert for the array list, I said order in is what we're going to have to deal with, but in fact, because we're using an array, okay, and the array list presumably would have the ability to jump around on index, okay, like we can do with the get method. Presumably, we could take advantage of binary search to find the next insertion location. Okay, let me tell you why that won't quite work the way that I want my priority queues to work. Okay, and it has to do with this. What happens when I have items in there? In fact, we can go all the way back to our example here. And let's put in, whoops. Let's copy S and put some more of them in there. Okay? So I've got some duplicates in there, and when we compare those to each other, we're going to get zeros. Okay? The comparison is going to give 0 because they're exactly the same. So the feature that I want my priority queue to have related to duplicates is I want it to enforce FIFO for duplicates. That means, and our array list isn't going to do that, okay? That means, where'd it go? That when I start pulling stuff out, so at first I expect B to come out, that's the smallest, then H, then M, then I expect this S here, first duplicate out. That should be the first one out. The first S that was placed in should be the first one out. Because remember, it's possible for me to have the keyed item is only the key. It's part of what's going to eventually be a more complicated object. It's not right now. It's just a string. Okay? It's the identifier for a more complicated object. In general, we could have the identifier match. Okay? For different objects that have all kinds of other different information, they could, in principle, have the same identifier. Okay? So, if we were building a database, we wouldn't have unique identifiers, but that's not what we're doing here. Okay? And so then I would expect this S, which was the second one in, second duplicate out. And so if we draw a picture of what happens when we try to use binary search. And we've got those S's in here. Let's put a bunch of them. I don't know where binary search is going to compute that midpoint. Okay, depending upon how many elements are off to the left and how many elements are off to the right, this could be the midpoint. So if I come in with another S that I want to place in this thing, I don't know exactly where it's going to end up in this long list of S's. Okay, it's really supposed to go to the end of the S's. Okay, but if I'm using binary search and I compute a mid, it's going to go somewhere in the middle. So in the case of binary search, we would not be able to guarantee, we might get lucky and work fine all the time, but we can't guarantee that we're going to have FIFO for duplicates. On the other hand, if I use a linear search, can I guarantee FIFO for duplicates? Yeah. So I simply find where my first location of S is, okay? And depending upon where I'm pulling items from, I think we decided it was going to be the end. If I'm pulling items from the end, then I want to go to the other end. No, that's not true. If I'm pulling them from, the smallest item is coming off the end of the array, this one's going to come off first. So I want to put my new S there. So as soon as I find where those S's are, okay, I got a 0 for my comparison, well, now I know where it goes. So I make room for it and I put it in that spot. Okay? So that way the very first S in is going to be the very first one out. And that will be true of all of these. Okay? There's a lot of cases where you don't care about the order of the S's, in which case, a binary search would be fine. But there's a lot of cases, particularly, programming assignments, where FIFO for duplicates does matter. In fact, I can give you a specific example that comes from a later lab. So we have those player turn orders, those 4 slots for red, green, purple, green, and yellow, and we've got the amount spent blocks. Okay? And what if these are all ties? So let's suppose everybody spent 5 that last round. So we've all tied an amount spent, and currently, red went first, then yellow, then green, then purple. Okay? In fact, let's make one of them not be. Let's make, so this is red, purple, green, and yellow. Let's make this one be a 7. Okay? So we're going to sort, and we expect the order to maintain FIFO for duplicates. So if you are already earlier in the turn order and you're tied with a bunch of other people, we expect you to stay at that spot. Okay? So, in fact, yellow was next. So yellow is going to go here. It's going to maintain its spot. Purple and green are going to shift position. And green is going to end up last. So anyone who's tied needs to maintain their current order. So these are duplicates. So essentially, our keyed item in this case is the 5, the amount spent. Okay? They are identifiers for very different objects. The players have completely different setups. They got different cards, different tokens. Everything's different. But their identifier is the same for purposes of this particular sort. Okay? And so I need, if I want to use some code that I've already got written, like PQ sort, I need to make sure that it's built using FIFO for duplicates, or the red, yellow, purple order is going to be arbitrary. Okay? Again, many times I may get lucky and have it work, but eventually I'm going to come across a case where it doesn't keep the ordering correct amongst players that all spent the exact same amount. Okay? So when I talk about FIFO for duplicates being important, generally speaking, for many applications it's not. But for a lot of stuff that I've had to do, stuff I put on exams, personal projects I've been working on, it's just better to have all the features available. So build it in from the beginning, the maximum set of features that your priority queue needs to support. So use an AVL tree or something. That you can make an AVL tree, keep FIFO for duplicates. Okay? There was one more thing I wanted to mention, but I forgot what it was. I cannot remember what it was. So what would our ordering be if red also had 7? And this is the original ordering. So purple and yellow are going to go before red and green. Purple is currently after yellow, so yellow will end up first, followed by purple. And then red's ordering relative to green has to be maintained. So that would be the correct ordering. Okay? Oh, yes, I do remember what I wanted to say. So just like we've got an array list that we've utilized, built, provided by Java, it's got other stuff. It's got trees and other fun stuff like that. Okay? However, I frequently use the stuff that I wrote for data structures rather than the built-in classes that Java provides, because they frequently don't have all these features that I know would not be a big deal to put in there. Okay? If you use the priority queue, the built-in priority queue, let's see how much you remember from data structures. If you use the built-in priority queue, it's built using a heap, which I hope most of you at least recognize that term. Do you think a heap allows for FIFO duplicates? Not probably the way you studied it. You could modify it to do more complicated stuff and make it work. But the way you cover it in data structures, the way you most likely cover it in data structures, is when you insert a new item, it goes at the end, and you've got to swap to figure out where it goes. Well, hopefully you remember when you talked about sorting, that if the sort has swaps, then FIFO, that you don't maintain the ordering of elements that are equal. They can exchange position. So in a heap, when you're swapping items, moving from the bottom to the top, same thing can happen. So in a lot of built-in data structures use the heap, because if you omit that one feature, other than that, it works great. It's very simple to understand. Okay? But it can't easily handle the FIFO for duplicates feature. Adding that into an AVL tree, it turns out, is pretty easy. Okay? We can make sure, let's do that. MBZ. Okay? It's going to be really easy for me to figure out where another M should go so that this M, which I'll call M sub 1, is removed first. In fact, I don't have to do anything new, essentially nothing new. Whenever I see a comparison and I get a 0, go right. That's it. Okay? So if I do that, then I'm going to end up with M2 here. When I remove items, M1 is going to come off first, and M2 is going to come off second. Okay? All right, see ya.